Hello everyone, this is Dr. Marina Nawal Sabra from the Lebanese University. In this chapter, we are going to explain the binary numbers. We are going to introduce binary numbers, talk about the digital form. We are going to talk about the representation in the binary form and number conversions between the three different bases, decimal, binary, and hexadecimal. Define what hexadecimal is. We are going to talk also about uncertainties in binary representation and their effect on the measurement, and about binary codes. Binary numbers are the way the computer understands data. So as humans, we refer to the decimal base, that is base 10. And in the computer, because the computer only understands current passing or current not passing, so it has two different states to represent the data. This is why we mathematically represent the information we want to put inside a computer or a PLC or a microcontroller or any system that uses the computer logic in base 2. So when we use a computer, this is very important to learn base 2 and the binary logic. So some advantages or some applications of binary is everything that is digital. So every time you hear about something which is digital, this means it is based on binary language. So we're talking about calculators, machine simulations, artificial intelligent machines as well. Audiovisual transmission, when they talk about digital, this means they are converted into binary. When they talk about analog, this means they are not converted to binary. So, so many advantages of using the digital world. So binary has two different states. So just as base 10, we go from digits 0 to 9, and binary have digits 0 and 1, where 0 stands for off and 1 stands for on. High voltage means inside the computer it is 5 volts, and 0 it is 0 volts or something very close to 0 volts. So the binary number has only ones and zeros. So if we look at this, you can see that it should be a binary number. It doesn't mean that every time I see ones and zeros, it means that the number is binary. It could be 1001, 111. So to differentiate between a binary number and a decimal number that could contain only ones and zeros, we refer to the numbers with an index, where index 2 is for binary and index 10 is for decimal. If I want to understand the value of the number in binary, I have to remember first that when I had a number like 7492 in base 10, if I wanted to use it in the expanded form, this is what it gave. It gives the digits times the powers of 10, because 10 is the base, of the different place values of the digits. We are going to do exactly the same for binary. So we are going to multiply the ones and zeros by digits and powers of 2's in this case with their place value. If I multiply these out, it is my way of transforming a binary number to a base 10 decimal number. So 10101 is 21 in base 10. So representation in a binary form, so I can represent any number in the binary form. I can go for other representations. Who said I have to represent everything in base 10 or in base 2? I can represent in just any base 4, base 8, base 5, but representation mathematically in other bases, they have no uses, except for base 16. Why base 16? Because 16 is itself a power of 2, just like 4 and 8, but we consider base 16, which we call the hexadecimal base, as a reference because it is exactly 4 digits and it was chosen for representing a binary number in a way that is readable to humans. Because if you want to look at a binary number which is very long and full of ones and zeros, and you want to analyze a series of values, it becomes way too complicated for humans to read them. So this is why base 16 comes into handy. We're going to discuss base 16 in this part. So when I want to convert numbers between decimal and binary, I already saw how to convert a number from binary to decimal. It was by multiplying out powers of 2's. So to convert 25 back to its binary value, I expect to divide by powers of 2. So this is what we would have. We have 25 divided by 2, we have a value and we have a remainder. And the remainders are the actual binary numbers. So I take successive divisions by 2 and I get the whatever remains, and I go from bottom up because this is the lowest value, the lowest weight, and this is the highest weight, and I get the 11001 number in binary. So I converted between decimal and binary and decimal. What if I had a decimal point and a part after the decimal point? So if I want to convert from binary to decimal, I just continue by multiplying powers of 2's, but in this case, I continue subtracting 1 at every power, so I get negative powers of 2, and this means I'm dividing by powers of 2. To convert the decimal part from decimal to binary, inversely, I will have to multiply successively by the digit 2. So I take the decimal part, so if I have a number which is 25.367, I take the 25 and convert it, and just like I explained in the previous slide, to binary, and then I take the decimal part and just go multiplying that by 2, and I keep the whole part, and this is a binary number, so this is decimal part within the binary number. So as you see, converting between decimal and binary is something that takes a lot of calculation, so it's a heavy process. If I want to just represent my decimal number in a binary form, it is difficult. So instead of representing or converting a whole number to binary, if I don't want to do any calculations inside, it is better to just, if I have a binary number and I want to read it on a screen, I can just convert it. Instead of converting it to base 10, I would convert it to base 16. So let's look at base 16. If I take exactly 4 digits in binary, every 4 digits are exactly 1 digit in base 16. So they go from 0 to 15 as a value, and to represent them in base 16, I'm going to borrow from base 10 all the digits it can give me, and then I can borrow from the letters for the rest because I need one figure for each number. So I go from 0 to F, which represents 15, and if I want to convert a number between binary and base 16, is going to be straightforward. Going from base 16 to base 10, I can, just as I did in the binary, I can multiply by powers of 16 and I get the base 10 value. If I want to go between binary number and base 16, I can go from the decimal point and just choose every 4 digits and transform them either on the table or calculate by using the weights, and I can find the digit, the corresponding digit that it is in base 16. So I don't need to convert these 4 digits as a real conversion to hexadecimal, just as I did in decimal form. I take the 4 digits, I look at their value, and I just put them next to the 9 that is corresponding to the other 4 digits. If I had to convert this number to decimal, for example, I will have to multiply each digit by the exact power of 2. So if we go from 2 power 0, 2 power 1, 2 power 2, 2 power 3, and here we go to 2 power 4, 2 power 5, 2 power 6, you're multiplying with numbers in the hundreds. Whereas in here you go back to multiplying 2 power 0, 1, 2, 3, and then again 2 power 0, 1, 2, 3. That's 1, 2, 4, and 8, which is simpler, much simpler to calculate. You can also take them from the table. So you end up with a value that is easily converted. So inside the computer to represent on the screen values that are human readable and are binary at the same time, it is much faster to go for hexadecimal than go for decimal. The only thing you have to note that at the edges, if you don't have exactly four digits, you have to add zeros. To the left side, it's not all that a big deal because you can see 110 is 6, so you don't confuse. But at the right side in the decimal part, looking at a binary value which is 1, 1, you can easily mistaken that for a 3. Whereas if you add the zeros, you can pay attention and know that it is a C. This means it's an 8 plus 4, that's 12. Moving to uncertainties. When I talk about uncertainties in binary representation, I talk about how much place in the computer memory I allocate to put this value. I am taking in the next slide an example. So the precision is really related to the space allocated. I'm transforming an analog value, which is the exact physical value, to a number of digits. So I might be losing some of the precision. To define here, a byte, when you talk inside the computer, is 8 bits, a word is 16 bits, and we can go up to 64-bit representation, even double that inside the programs if we need to. So as an example, I take the number 13 divided by 3 and want to store the answer. So it is 4.3 dash, that's an infinite value. If I consider 6 digits to represent it in binary, the value is transformed. You can transform it yourselves in the method we just explained. It is 101011 in binary form. If I transform that back to decimal, it is 4.3. If I consider 10 bits this time to represent the same number, I have a longer value, and if I convert it back, it's 4.33. So I gain in here 1 decimal digit precision. This means that if you have a measurement and the value you are looking for is at the second digit after the decimal point, if you look into a coding in 6 bits, you might be losing the information you set up your experiment for at the first time. So if you have a very important, precise setup, you need large number of bits. This is in the what we call the data acquisition and in the storage memory to be able to save, transmit, and save this value to keep the precision that you have set up for and you have paid for. The binary codes. Well, sometimes I do not want to analyze a value. I just want to transmit it, like when I'm talking about audio-visual video transmissions. In audio-visual video transmissions, I just want to transmit values from one side to the other. So I don't need to understand them. I just need to code them in binary form. So this is why we have a very big set of binary codes. These are the basic ones that I'm going to explain in here. The first one is the simplest one. It is called the binary coded decimal, and it's the 8421 weights. These are the exact power of 2s that we were looking at in transformation to hexadecimal and in the decimal to binary transformations. So if you look in here, these are exactly the values. Take any number. This is 101. So this is times 1. This is times plus 0 times 2 plus 1 times 4 plus 0 times 8, and the result is 5. And this representation is exactly representing the 5 digit in decimal. This means that it is the binary value representation. The difference is that if I want to code a number that is 7895, I do not transform the 7895. I transform each digit alone and transmit it and then receive it on the other side. Since I have 16 possibilities and I'm only using 10 of them, we have the possibility of making modifications. The first modification is, instead of using the 8421 weighted values, I can use any other weighted value. I can, for example, in here we have 6311, so I have the first value Every time I have a digit, I'll have to fill up from right to left to avoid having any confusions. So in this case, the 2 is coded in 0011 because it is 1 plus 1 plus zeros. The 3 is in here, and this is 3 plus 1, 4, and so on. The only condition that we have on this kind of codes is that every digit should be represented. I would have to be able to represent all the digits and be able to represent them in a unique way. So you have to remember to begin from the right to the left so that it is always one unique representation for every digit to avoid confusions. Another way is the XS3. XS3 is the 8421 code itself, but we shifted by 3. So you can go look from this value onwards, they are exact copy, and then you have 3 extra values, which in binary are 10, 11, and 12, but in here they are the codes of the decimal digits between 0 and 9. Another interesting code is the 2 out of 5. So in 2 out of 5 code and in XS3, we don't have series of zeros because sometimes when you code images, we have a lot of black, and black is represented by a 0 value. So you get a long series of zeros, and this is prone to errors, so it can create errors, and this is confusing sometimes. So to avoid this, some of the codes just avoid the 0 code for the 0 value. 2 out of 5 does not only do this, it also allows debugging. What does that mean? It is true that 2 out of 5 represents the value in 5 digits instead of 4, so it's more costly. But at every time we receive on the other side one of these values, we have to check, we can check that 3 of the bits are zeros and 2 of them are ones. You just take any digit in here, it has 3 zeros and 2 ones. It is filled up from right to left. So if you look in here, we have the 2 ones, and then we shift one of the ones. So I have a process of filling it up. But at every time I receive on the other side, I can always verify. Whereas on the other codes, I cannot verify if I have an error in transmission. An error in transmission means when I'm sending the message, I can have a phone ringing, a microwave passing through the transmission line, and it can change one of these zeros to 1 or one of the ones to a 0, and it can change the value itself. If I am by chance transmitting, let's say, a bank code or something like this, something that's very serious, changing one of the bits, one of the digits would be really, really very harmful. So, of course, this is one of the simple ways of verification. In banks, we use more and more of these verification methods. Gray code is mainly used in industries. I have an example on the following slide to explain gray code utility. The gray code has a special feature in that we only change one of the digits when we are moving from one value to the other. So in here you can see that every time I have 3 zeros, this bit is changing from 0 to 1. In here I have only this bit changing value, and so on. If I look at this example, this is the binary code itself, the BCD code, and this is the gray code. This is an encoder, and the encoder it has 3 sensors, where each sensor is a lamp, and if the light is passing, this means it's a 1, and if the light is not passing, it means it's a 0. If I want to go from one value to the other, if I have gray code, I am sure to not have glitches. What is a glitch? A glitch is a value that I do not want. That when I am going from 100 to 101, I don't want any other value in between. So if the lamps are a little bit shifted one from the other, and here I don't have any problem because I only have one value changing. So it's either taking 100 or 101. But if I have, for example, a value between 011 and 100 in here, so I'm looking for it. So if I have this value changing, so you can see the first, the second, and the third values are changing at the same time. So if one of the lamps gets its value before the other, I can just have 001, and then I can change into this. So I have a change of value. When I go back to the computer and interpret this, The encoder codes at every time a change in position. So if I give it a wrong value, it could imagine or understand wrongly that it has moved a whole circle and came back. And that is why encoders are also always coded in the gray code form. To end with, I have the ASCII code. It's another example of binary because it's a very long code. That's why we don't have it in the slide. We just have a small part of it. It's an 8-bit code, a 7-bit plus one verification code, and we have ASCII code. You could represent all the keys that you have on the computer. For example, it's a standard code for representing all the digits that you have and all the letters that you have on the computer. This is a slide where you have some exercises on the homework. You're also going to have them in the slides, and I would like to thank you.